Okay, hello everyone. Good morning and welcome to this month's COFFIES Seminar. Today, we have a special seminar arranged for the COFFIES Butterfly project led by Andrés from Southwest Research Institute, who is also part of COFFIES. And I assume at this point everyone knows Andrés well. So I will pass this Zoom to Andrés now. Andrés, you have the Zoom now.
Thank you so much. Okay, let me share my screen. Okay, so I am very proud to get us started. As you may know, we are the Butterfly project. We have an objective, a technical objective of creating a solar butterfly wing generator, but we are a social experiment into how to do cutting-edge research in a way that combines education and leverages AI assistance. So we had, you will hear a lot more about our programs, who we are, etc. But I want to introduce you first to the people whose voices you will hear today. After I speak, I give you a quick introduction. You will first hear from Phoebe and Claudia. They were my my left and right hand for this project. And it would have been impossible to coordinate and organize the program without them. And then you will hear them in this order: Swaksh, Myra, Jessica, Oana, and Allison. They were all participants, active participants to the program, and they were the people that wanted to make this presentation a reality. I want to say you can see that their backgrounds cover everything from high school to postdocs, and I will say that I will hands down recommend any of them for any position that you may consider. They are amazing, they are engaged, they are responsible, they always deliver, they were always there, and they made this program the success that it was. So if you ever have any questions about any of them, just let me know. So I will start with a take-home message. AI assistants are a tool that is increasingly used in all aspects of human endeavor, and this brings challenges and opportunities, and this program is our proposal to how to take advantage opportunities while offsetting and overcoming some of the challenges. The underlying concept here is when people interact with AI assistants, typically they think that the way they prompt the assistant to give them help them accomplish a task is the real skill. In reality, is the classical education, your conceptual vocabulary, what is your limitant? And so we have built the whole program exactly around that concept of vocabulary. So Butterfly is a voluntary class that leverages assistance with two kind of broad objectives. One is teach them and teach participants with very diverse background, classical and AI assisted statistical modeling. And the second one was to demonstrate that we can achieve better scientific outcomes than those available to the most proficient researcher in the collective, which in this case was me. So I would like to emphasize that our models, our best models, were better than the model that I came up with myself. It was the fact that we were all exploring similar concepts with the help of the AI assistants that really allow us to explore many possibilities and obtain something better than what I could have accomplished myself. We had two technical goals: develop a solar cycle hemispheric wing generator that only uses cycle amplitude as input, and develop an AI assistant correction to that classical model that creates more realistic hemispheric wings. So you will hear that from our presenters. So to start with is this idea that AI is increasingly part of human effort. I just wanted to show you this little plot that shows the adoption in software engineering of AI assistants. That in 2025 was already, at the beginning of 2025, was already at 84%. This was a survey made by Stack Overflow. At this point, probably we're in the 90s%. And so, this is there is true value that the systems add to our ability to accomplish tasks, but there is also a challenge, and that is the idea of cognitive surrender. So when you think about cognitive psychology and how human cognition interacts with information, is basically composed of two types of processes. One is that people call system one, is fast, intuitive, and associative. This is almost, we get it for free, is active almost all the time, and doesn't require a lot of effort. And the overwhelming majority of the way we interact with information and make decisions is using this system. The second one is system two, which is slow, reflective, and rule-based. So this one is effortful. You need to engage on purpose with it. It can be triggered by things that don't quite add up. And so your brain switches from one mode to the other. So when you're reading or hearing a presentation, you're typically in system one. But if there is something that doesn't quite add up, you're like, wait a minute, I don't understand this. That is where systems two come into place. A huge part of our cognitive biases exists in system one. And when you're addressing cognitive biases, that's kind of like this, you have to negotiate the transition between one and the other. But the issue here is that we now have an external system that is joining the cognitive exercise, which will be a system three, artificial. And the reason is that AI is a reasoning system. The way the models are trained to present arguments is reasoning, and we perceive it as logical. And so if you're engaging with an artificial intelligence assistant, and you're mainly working out of your system one, which is fast, intuitive, and associative, there is always the risk that you will accept the logic of the AI as your own. And that's what we call cognitive surrender. So the idea is that you have to put yourself and your assistant guidelines or guardrails that help you offset and address and manage the risk of cognitive surrender. But this is a hard thing to do. So it requires you to be effortful, and it requires an energy cost. So the challenge for our training pipelines is that in the past, we had mentors that were assigning tasks to mentees. And the mentee will go research, implement, and go back to the mentor with the result. But now we have a mentor that assigns a task to a mentee, which makes an imperfect assignment of that task to AI. Then this AI implements, and the person goes back to the mentor. But the mentor is handling then two challenges. One is explaining the task to the mentee, and the other one is the broken telephone that happens between the mentor and the AI. And this creates an incentive to basically remove the mentee out of the picture, because the mentor can give the tasks explicitly and directly to the AI without that loss of precision and information. So the idea of ButterflAI is that when we are mentors and we have a task, we are dealing with a coupled system. We have mentees with AI assistants, and as mentors, we need to provide instructions for both. So we need to teach our mentees concepts and vocabulary, and we need to provide our mentees with prompts that model the way a professional or a high-skilled user will give to the AI. And that allows to create this kind of virtuous loop where the mentee, with the help of AI researchers, and implements and produces an output. This output then can go back to you as a mentor. And specifically in ButterflAI, what we were exploring is the possibility of a single mentor having many mentees, thanks to the fact that they are all working with AI. So now you can have an arbitrary number of mentees, each one of them with an AI assistant, and each one of them producing a slightly different output. And that is a powerful thing, because driven by the curiosity of each mentee, you will end up with very different realizations, all effective, all addressing the task. But then the mentor can consolidate and end up with something better than what the mentor could have accomplished. So you have an incentive now as a collective, you have a benefit that you had lost in the previous picture. So we are basically defining the idea of the collaboration scale, where you go from level one, which is creative subordination. You have a limited vocabulary and your ability to recognize errors and etc. is very limited. So the AI fills a lot of gaps for you in a statistical way. And as you improve your vocabulary and concepts, you start displacing yourself through a scale in which gradually you have more and more agency compared to your AI assistant, to the point where when you reach what we call equal partnership, you could do the task yourself. You don't need AI. You have understanding of all the concepts, you have all the competences, and you could implement it to yourself. And that is actually where we all want to aspire to be. That we could do the task ourselves, but AI allows us to do it faster and potentially have access to ideas that we normally will not have thought. So we all need to work actively towards moving in this partnership. So the idea is that to create something that we call the bootstrapping, the dialogic bootstrapping cycle, the person prompts, and then the machine, instead of filling all the gaps silently and giving an answer, you recondition AI assistants so that they actually identify the terms that the user doesn't know but needs to understand to understand better the task. And then it will create a friction, push the user to identify and internalize these concepts so that they refine their vocabulary and you can then prompt better. So this is possible because large language models are ideally trained to meet you at where you are. The problem is that they're trained also to silently fill all your conceptual gaps, but they can be reconditioned, and that's part of the task. So when we do assist AI in the classroom, the idea is that we need to first focus on building the vocabulary of our students, provide tasks and prompts. So we need to show the students how we prompt the machine to produce the outcomes that are like best possible outcomes of the task, but also show them how we use our own vocabulary for that task completion. We need to enlist the students so that they understand the idea of the AI collaboration skill and they can take action. They can make their own the journey of becoming more and more equal partners. And then we use the AI assistants to create the friction, to force the students to use new vocabulary interactions, etc. So if you're curious about the prompts that we use, you can look at them here. And if you have more questions, you can ask me. But now I will give the floor to the rest of the collective that will tell you about the program and our technical accomplishments.
ButterflAI began as a research project within HelioHub, the Discord-based community for undergraduate students, recent graduates, and early career professionals interested in heliophysics at any level. HelioHub was established through COFFIES, a NASA-derived science center, in May 2025, with the goal of making the heliophysics community and its opportunities more accessible. Through the Discord, we host webinars and workshops, share research and career opportunities, and create spaces for members to connect with one another. After the first summer of programming, we surveyed our members to better understand why they joined HelioHub and what they hope to gain from the community. Most respondents were undergraduate juniors and seniors, and we saw a few themes come up repeatedly. Members wanted to learn more about heliophysics, but also specifically wanted research experience and practical technical skills, requesting topics on where to access solar data and how to process and analyze it. There was a strong community component as well, with members wanting opportunities to meet others interested in heliophysics, build their networks, and practice communicating their research. With these results, HelioHub worked to provide just the opportunity its members were looking for, a community research project designed to be accessible regardless of a participant's starting level of technical or research experience, and so ButterflAI was born.
Before launching ButterflAI, we surveyed prospective participants to understand their technical backgrounds and design a project that would be both accessible and challenging. We received 31 responses. Looking first at AI and machine learning experience, over 1/3 of students had no prior experience, while another 39% had only basic familiarity with classical machine learning techniques, such as regression or clustering. Only about a quarter had experience training neural networks with frameworks like PyTorch, and very few had previously built end-to-end machine learning pipelines. Most students had intermediate Python experience, while 16.1 were advanced and 12.9 had only basic experience, while only 6.5% had no prior Python experience, indicating that the majority entered the program with some existing programming skills. While most students had intermediate Python experience, nearly half had only basic GitHub skills, and almost 1/4 had never used GitHub at all. These results highlighted that many motivated students are interested in AI-driven research but lack experience with the tools typically expected in research environments. This directly shaped the structure of Butterfly. We began with foundational workshops in Python, GitHub, and machine learning before gradually building towards students contributing to a novel heliophysics research project.
Before the project began, we asked prospective participants how much time they could realistically commit each week. Based on those responses, we designed Butterfly around a 4-hour weekly commitment. 2 hours were spent together in a synchronous Zoom session, and 2 hours were reserved for independent work on a weekly coding assignment. We also offered optional office hours for anyone who wanted that additional support. The research itself ultimately ran for 11 weeks. We spent the first 5 weeks developing the classical statistical model, and from there, we transitioned into the generative AI portion of the project, which built directly on that classical framework. Our original research schedule was 9 weeks, but as we approached the end, we offered an optional 2-week extension so participants could finish the AI model, evaluate its performance, and feel more conclusive with the project's final results. After the research concluded, participants who wanted to present the work met for another 3 weeks to prepare posters and this final presentation.
Butterfly followed the same structure every week. We met synchronously once a week over Zoom, where students learned new AI and machine learning techniques through short lectures and dialogic bootstrapping, a guided discussion approach that encouraged them to actively reason through new ideas rather than simply receiving answers. We also emphasized community building through network activities, collaborative Miro boards, and breakout rooms. Between meetings, students completed coding notebooks at their own pace. They were encouraged to use an AI assistant as a learning partner, not to generate solutions, but to ask questions, debug code, and deepen their understanding. This combination of structured live instruction and flexible self-paced learning made the project accessible to students with a wide range of backgrounds. Throughout Butterfly, we conducted 3 anonymous check-in surveys to understand how participants were progressing and to adapt the project based on their feedback. One of the clearest takeaways was how consistently positive the student experience was. Across all 3 surveys, participants reported feeling comfortable asking questions, supported by mentors, and engaged by the combination of live meetings and self-paced coding notebooks. This positive experience was reflected in how students felt about the project overall, with most students rating the project highly at the halfway point. By the final survey, 100% of respondents rated their overall experience a 4 or 5 out of 5. Mentor support was an especially strong part of the experience, with 88% of students giving it the highest possible rating at the halfway point. This remained strong through the end of the project, with every final respondent rating their support a 4 or 5. Students also responded positively to the project's mixed approach of lectures, activities, networking, team building, and AI-assisted learning. Engagement remained high through the final survey, where 100% of respondents rated the approach a 4 or 5, and 60% gave it the highest rating. These surveys also highlighted how participants' relationship with AI evolved. Early in the project, many commented that one of the biggest challenges was learning how to use GitHub and figuring out how to work effectively with an AI assistant without simply accepting whatever it generated. By the middle of the project, participants were describing AI as a collaborator rather than just a coding tool, and several rated themselves at the highest level of AI collaboration, an equal partnership, where they could guide the AI, evaluate its suggestions, and integrate them into their own reasoning. Final survey responses suggest that Butterfly successfully supported students' skill development, with 80% of respondents rating its impact a 4 out of 5. All respondents reported at least a moderate positive impact on their AI programming research or scientific communication skills. Finally, students consistently asked for more heliophysics, more statistics, more machine learning, and more opportunities to apply what they were learning to real research problems. Many expressed interest in extending the project, presenting their work at conferences, and participating in future Butterfly projects. By the final survey, every respondent said they would recommend Butterfly to other students. If you could just go next slide. Thank you. Finally, that interest was especially clear in our final survey. Every respondent said they would definitely participate in a second version of Butterfly. So we're excited to announce that Butterfly 2.0 will be launching this fall.
Since Butterfly was an open community project rather than a traditional course or research appointment, we needed a transparent way to determine authorship and acknowledgement. At the beginning of the project, every participant received an agreement outlining 2 ways they could participate, online or offline. Online participants joined the weekly synchronous sessions, while offline could complete the project asynchronously by watching the recordings and completing the same coding work. We then established participation thresholds for project credit. For online participants, co-authorship required attending more than 60% of synchronous sessions and submitting at least 60% of weekly notebooks to GitHub. Since offline participants didn't have an attendance requirement, their coding threshold was higher, submitting at least 80% of the notebooks for co-authorship. Participants who contributed meaningfully but didn't reach those thresholds could still receive acknowledgement with lower participation requirements for each track. After 11 weeks, 11 participants reached co-authorship status, with another 7 receiving acknowledgement for their contributions. These students will receive formal credit on any outputs from the project. Looking at the initial butterfly survey to look about these participants, we found they represented a range of educational backgrounds and starting experience levels, from high school to postdoctoral researcher. Our largest group of project contributors came from UC Berkeley. Given that HelioHub is coordinated through Berkeley Space Sciences Laboratory, many of our initial members joined through undergraduate mailing lists there. The project also extended beyond Berkeley, bringing together participants from 9 different institutions. Physics and astronomy were the most common academic backgrounds, which was expected for a heliophysics project. Participation was not limited to those fields, and we had contributors providing different insights from disciplines including zoology and botany. This demonstrated how AI could assist participants without an extensive heliophysics or machine learning background to still meaningfully contribute to the research.
To wrap up, these are the main final outputs from the Butterfly project. Our vocal framework paper has been submitted to Computers in Education Open, and a second technical paper covering both the classical and reverse diffusion approaches is currently in progress. Another major output is this final participant presentation at the COFFIES Seminar, where we're sharing the work and outcomes from the project. Finally, at the SPD meeting last week, we presented 2 posters, one on the classical approaches and one on the reverse diffusion approach. And Dr. Andrés Muñoz-Jaramillo and Phoebe Mahlin gave 2 related oral presentations, giving us several opportunities to share the project with the broader heliophysics community.
We will now be talking about the solar cycle, sunspots, the butterfly diagram, and the goal of our project. So first of all, what is the solar cycle? So just like any other cycle, like the rock cycle or the water cycle, the solar cycle is a series of events that happen over and over again. And it involves the sun's magnetic field flipping. So the sun's magnetic field is a key driver of the solar cycle. And in total, on average, it takes about 11 years for the solar cycle to happen and for those 2 poles to flip, which therefore means it takes about 2 solar cycles, or about on average 22 years, for the poles to return back to their original geographical states. So as you can see on the image in the bottom right, there are 3 kind of sub-images in that image. In the first image, we can assume that the blue lines are the positive pole and the red lines are the negative pole. So in the first image, the blue lines are the positive pole and they're in the north, and the red lines are the negative pole and they're in the south. However, as we move into the middle image, all of the lines are very tangled together and it is unclear where the poles are. But by the end of the solar cycle, you can see that the negative pole is now in the north and the positive pole is now in the south, as the poles have flipped with each other. And because of the solar cycle, there are many key patterns that happen. And one such pattern is solar flares. And solar flares are intense bursts of electromagnetic radiation, and they release a lot of heat and energy. So as you can see on the image in the top right, that is an example of solar flare. And they are very distinct, and because they're releasing so much heat and energy. Additionally, sunspots are a key pattern of the solar cycle. So what are sunspots? Well, sunspots are literal dark spots that appear on the sun. As you can see on these images to the right, the sunspots are much darker than the regions around it. In reality, if we looked at sunspots up close, they would be blindingly bright, and we wouldn't be able to distinguish them necessarily. They would still be very bright and hot. However, they are significantly darker than the surrounding areas on the photosphere, and that's why when we take these filtered images, they can be clearly distinguished from surrounding areas of the sun. And so why do sunspots happen? Well, sunspots happen because of the twisting of the magnetic field lines, and this blocks heat from reaching certain areas of the surface where the sunspots form. And that is why sunspots are so significant. Since sunspots are directly caused by the emerging of magnetic field lines from the surface, by tracking sunspots, we are able to indirectly track how the magnetic field is changing over time and in what areas it's changing. So now we have the butterfly diagram. And the butterfly diagram is a diagram that tracks where sunspots appear over the solar cycle. So as you can see in this image, each solar cycle has a distinct butterfly wing-like shape. And the x-axis in this graph represents the time, and the y-axis represents the latitude. So as you can see, over time, the sunspots begin at high latitudes closer to the beginning of the solar cycle, but then they get closer and closer to the equator as time moves on in the solar cycle. And the overall dominant pattern of all of the solar cycles is about the same because they all resemble butterfly wings. However, you can see that all the solar cycles are slightly different from each other and they're not exactly the same because nature ultimately doesn't repeat itself exactly. So what was the goal of our project? Well, the goal of our project was to fit statistical models to the butterfly diagram using both classical parametric and AI-assisted reverse diffusion models. Classical parametric models use a fixed set of equations to predict the next solar cycle. So they are very good at capturing the overall dominant pattern of how the next solar cycle will be. However, they are not very good at accounting for those deviations between the different solar cycles. On the other hand, the AI-assisted reverse diffusion models learn from the residuals between the classical parametric model prediction and the actual result, and based on that, they predict what the next solar cycle will be. And both of these models can then be used to generate synthetic solar cycles to fit historical data and forecast the future.
To build our parametric model, we focus on two primary features of the solar butterfly diagram: equatorial migration and latitudinal spread and density. To track the equatorial migration of sunspot groups, we examine the path of sunspot emergence as the cycle progresses. As shown by the mean trend lines for solar cycle 24 in the figure on the left, sunspot groups migrate from mid-absolute latitudes towards the solar equator as the cycle progresses. Then, using kernel density estimation, we examine how sunspot density changes over time. As is seen in the figure on the right, the active zone doesn't remain static. Rather, it expands latitudinally during the growth phase and contracts during the decay phase, thus capturing the changing width as the cycle progresses, a feature needed to model the full 2D shape of a butterfly wing. To compare and fit multiple solar cycles simultaneously, we first need to standardize time across the cycles. One thing to note is that since the path of the sunspot groups and the shapes of the wings are not symmetric in the northern and southern hemispheres during the same cycle, our solar cycle generator will be fitted using cycle hemisphere pairings. So the first challenge that we faced was that solar cycles vary in overall duration and start times, making raw calendar dates difficult to use to make a direct comparison. Thus, we chose 15 degrees in absolute latitude as our alignment anchor. For every hemisphere cycle pair, we define tau as the exact moment its mean sunspot latitude crosses 15 degrees. Thus, this tau measures years relative to the 15-degree crossing, as seen in the scatter plot to the right. As seen in the scatter plot, aligning cycles by this tau allows the wings to be tracked along a single standardized timeline, enabling us to focus purely on physical cycle progression. With time standardized, we began to model two variables of interest: mean migration path and active zone spread. First, we fit an exponential decay curve to each hemisphere cycle pair. The parameter A fixes the mean latitude at our anchor point, while B controls the rate of equatorial drift. Then we averaged the individual exponential fits, which yielded the ensemble mean path shown by the thick black line in the top plot. To then model the changing wing width, we fit a split normal curve to each cycle. We selected a split normal because active zone expansion and contraction are asymmetric, meaning the wings fan out rapidly during the growth phase, but decays at a different rate. The resulting fits are shown in the bottom plot on the right. While this initial model captures basic migration and spread, we need to refine these models in order to build a more accurate predictive template. To build a robust generative model, we refined both components to establish a master wing template, which are the universal mean path as well as the tau variable, and how we track the spread of sunspots. For the first component, we pull all historical cycle data to fit a single universal mean path. To do this, we adjust each individual wing along the timescale to find the refined tau offset that best aligns the wing with this universal trajectory. As shown in the top plot, this significantly tightens data alignment across all of the cycles. For the latter component, we replace the time-dependent split normal with a piecewise linear model based on mean latitude rather than time, as the spread depends on the state of the solar dynamo. This means that we expect two cycles reaching the same latitude to share similar active zone widths regardless of timing. As can be seen in the equations to the bottom right, for the decay phase, we use universal shared parameters because all wings collapse in a similar manner. However, for the expansion phase, we use cycle-specific parameters because the initial wing expansion depends directly on the individual cycle strength, as will be expanded on later.
Now, since we have the synthetic wing shape defined through statistics, we need to bring one last yet important parameter, the cycle strength. Our end goal for the classical model is to synthesize a solar cycle from a single input, the solar cycle strength or amplitude. Before we move forward connecting our wing parameters with the cycle strength, we need to transition away from the typical wing model, where we have time versus emergence latitude, to look at the morphology of the active zone. So let's dive into the complexity of what Myra shared with us. Here's the same figure that Myra discussed with us before, but now we need to view the wing from a different perspective. I have overlaid a variation in spread of the emergence latitudes, or the active zone, over the full solar cycle, and I color-coded two important regions for us, the wing growth and the wing collapse. You can note through this simplified visual that the spread of the active zone varies across time and cycles, but we need to remove this time dependence. So let's return to our piecewise linear function. This is the same figure that Myra showed us with the time versus sigma, or wing width, fitted with a split normal function for every hemisphere cycle pair for the universal fit. But let's step even further. Using this universal fit, we can translate our figure from the time to latitude. Here we are looking at how the width of the wing varies across different mean emergence latitudes. Although this figure looks the same, it actually isn't. This allows us to focus on the state of the dynamo and not the calendar. So breaking into this piecewise linear function into its separate components, we can highlight the wing growth and the wing collapse separately, as in this figure. The universal wing collapse function is the red dashed line. The individual wing growth bits are the solid color-coded per cycle lines that are on the left side of the figure. So now that we have our wing parameters based on the state of the dynamo instead of the timing of the solar cycle, we can tie in the solar cycle strength. The solar cycle strength is derived from the daily corrected sunspot area. So we collect the maximum values for each cycle derived utilizing a 12-month rolling average. We then compare them with the wing parameters that we just established. As a reminder, the parameters are mu naught, this is the highest mean latitude that the cycle has sunspot data, so the earliest emergence. Mu peak, this is the widest point the wing shape gets before the collapse towards the equator, and M of I. This is the slope of the function representing the wing growth side of the piecewise function. Now on the left figure, we have the highest mean latitude versus peak amplitude. A positive slope here indicates a positive correlation. Stronger cycles on average will have higher initial emergence latitudes. This is where the wing growth begins. Now, the middle figure highlights a positive correlation for the detachment latitude, where stronger cycles will detach from the wing collapse side of the function earlier. Stronger cycles maintain their active zones for longer durations in comparison to weaker cycles. Now, using the same figure as before, the blue box highlights a few examples of where stronger cycles break away from the universal fit, that red dashed line, at higher latitudes to follow their own growth patterns. This is the point where the wing has reached its maximum spread or the widest active zone. Now, the right figure shows the wing growth versus peak amplitude. Although the correlation is not as strong as the other parameters, the positive slope indicates the stronger cycles have steeper slopes in the piecewise function. Or you can think of it that the active zone expands faster for stronger cycles. So the pink arrow here is highlighting various cycle-specific slopes for the wing growth side of the function. In general, the steeper the slope, the stronger the cycle. So now, since we have the full parameter space, we can generate a full synthetic solar cycle with one input parameter, the amplitude. We can use cycle 23 as an example. For step 1, we use the universal mean path to estimate a yearly mean emergence latitude for the full cycle. For step 2, for the input parameter, the peak cycle strength, we can use the wing parameter relationships that we just discussed to estimate 1, the maximum initial latitude, 2, the detachment latitude, the widest point of the wing, and 3, the poleward slope of the wing growth. And then step 3, for each year's mean latitude estimated in step 1, we estimate the spread using the determined piecewise linear function fit from step 2. And combining these two steps, we get a yearly Gaussian fit, which represents our synthetic solar cycle, which you can see here at the bottom. So let's look at this result even closer and compare to observations from cycle 23. So the figure here shows the sunspot data for the full cycle of 23. We can compute the kernel density estimate for 1 year. So the solid and shaded region indicates the spread of emergence latitude for that year. The dashed line shows the mean emergence latitude. We can then do this for the entire duration of solar cycle 23. Note the equatorward drift that we expect and how each KDE varies in structural distribution throughout the solar cycle. Now, using the classical model, we can predict the butterfly wing for cycle 23 and see what it will look like solely based on one input parameter, the cycle strength. So following the steps of the classical model, we can establish the mean emergence latitude for a single year using the universal mean path. Using the amplitude, the peak cycle strength, we can determine the relationship to the wing parameters and establish the piecewise linear function that is appropriate for cycle 23. So using this information from the previous steps, we can estimate the spread of emergence latitude for that year. Overlaid on the KDE for the year 1997, you can see the corresponding blue shaded Gaussian that is outlined by dashes. We can follow this procedure for the full duration of the solar cycle 23. So note how the fits are in relative agreement, yet the Gaussian fits lack the fine, sometimes bimodal structure that you can see in the KDE profiles. This is especially relevant for the early and late years of the cycle. So let's discuss the strengths and weaknesses of the classical model. The classical model captures the equatorward drift quite well. It also handles predicting the yearly mean emergence latitude and the global evolution of the active zone pretty well. Where the model does not succeed is capturing the anomalous cycles, the yearly fluctuations, and the bimodal distribution beginning and ending of these cycles. Essentially, we need to consider additional parameters that take into account hemisphere asymmetry, cycle overlap, and early cycle scatter. Unfortunately, these are more challenging to define mathematically. This is where AI can be a great tool in our belt. AI can then learn the microstructural details that the classical model, which is purely based on linear fits and Gaussian fits, leaves behind. So moving forward, we will leverage our AI reverse diffusion model to make corrections to our classical model.
So, as mentioned in the previous slides, the classical model misses a lot of various features such as hemispheric asymmetry, cycle overlap, and early cycle scatter, to name a few. And the reason for this, as mentioned, is structural. It only places one Gaussian per year per hemisphere. So whatever the real distribution looks like, a Gaussian is what will come out. The figures on this slide show what this might look like on our data as well. So both figures plot absolute emergence latitude from 0 to 45 degrees against normalized density. Magenta bars are observations, and the black curve is the classical prediction for that window. On the left is is one window from cycle 23 south, which contains about a few dozen sunspot groups. And we can see that there is a disagreement between the observations and what the classical model predicts. The tallest bar near 30 degrees is about twice the height of the Gaussian underneath it. On the right here, we have all 232 training windows average. So this includes cycles 12 to 24. And now there's plenty of sunspot groups for the shape to be stable, but the disagreement is still there. For instance, there's extra density between 5 and 15 degrees and a deficit from 20 to 30 degrees. So we can see that there is a lot there still is a disagreement, even with the average picture, which is more flattering. Essentially, because each hemispheric cycle leaves its own leftover, and those leftovers differ from cycle to cycle. And individual cycles are what we need to predict, and the classical model cannot express what it leaves behind. So we turn to a generative model, which will learn the shape from the examples without assuming a functional form. And to do this, we model residuals, and this is what we end up building next. So a generative model that's trained on exactly the part the classical model leaves behind. Because the classical model already recovers most of the distribution, we can keep that and just model the leftover. And the leftover is this residual, which is the observed minus classical, bin by bin, across 15 3-degree bins from 0 to 45, which is shown on the figures on the slide. On both figures, the y-axis is that a normalized residual. 0 means that the classical model predicted that bin right. Positive means observed density above the model. Negative means that it didn't predict the model. It didn't predict it correctly. And as mentioned previously, I wanted to iterate tau is a time measured from when a hemisphere's mean emergence latitude crosses 15 degrees. So a negative tau means it's earlier in that cycle. Positive tau means it's later. So on the left, we have one moment from cycle 21 showing both hemispheres, north in cyan, south in dark red. And they were both captured at the exact same time, and they have nearly identical amplitudes for comparison. And so because of this, the classical model should hand them nearly identical predictions, but the residuals still differ. And so this is hemispheric asymmetry in residual form. On the right, we have one hemisphere, cycle 23 south, at different moments in its cycle, but they both again have the same sunspot. They both have the same amplitude for comparison. The purple shows earlier in the cycle, green is later in the cycle, and we can see that earlier in the cycle there's an excess amount of predictions that sits around 16 to 20 degrees, but later sort of inverts, and there's a deficit near the beginning. So the residual depends a lot on the hemisphere and on its phase, and we have no close form dependence for either. And this is why the state of the cycle will now enter in as an input rather than an equation. And I will come back to what exactly goes into this equation. But after this, everything lives in residual space. So now we have the thing that we want to model, but the question is, how does a network learn the shape of that distribution? And that is what diffusion will answer. So here is the mechanism in general terms first before going to applying it on our data. So we're going to start with this COFFIES logo, and that's going to be a stand-in for our data. So on the far left, we have our original data. On the far right, we have noise. And in between are all the steps in this process. If we follow the top arrow from left to right, at each step, we're going to add a small amount of Gaussian noise to whatever came out of the step before. We notice that a single step barely changes anything, and you can see this between x0 and x1. However, if you repeat this 10 times, you're going to land all the way on the far right, where we drew a standard normal with nothing, and now we have complete noise. And notice the order things disappear first. The thin yellow rays tend to go first, but the cup and the lettering hold on much longer. So coarse structure survives noise while finer structure goes first. And that ordering is what the reverse process will exploit. So in the forward process, nothing is learned. There's no parameters. This is just a recipe for destroying data in a very controlled way. And because we add the noise ourselves, we know exactly how much noise goes in at every step. Now focusing on the reverse diffusion process on the bottom. We're going to go from right to left this time, and this is our model. So the network is going to look at one noisy panel, and it's going to predict that noise. It's going to subtract that position, and when you do that, we're going to go back to the previous step. And we're going to do it t times, and essentially we're going to have walked back from pure noise to something that looks like our data. And for us, our data that is being dissolved and recovered are these 15 bin residual vectors, but we're going to use the same mechanism. So here is a forward process on our real data. And here I'm focusing on cycle 23 south. It's early in the cycle. It's the same window as a couple slides previously. The top and the bottom halves are two different representations of the same process. So I'm going to walk y'all through this. So the top figure is going to be a heat map. We're focusing on one single latitude bin, 22.5 degrees, and it's tracked across all 232 training windows at once. The diffusion step is going to run along the bottom from 0 to 200, and the color is going to show where all those values live at each step. The histogram to its left is where the heat map starts. So this is the spread of all 232 real residuals in that bin. The readout above it is going to give you the step information and then the two schedule coefficients. Alpha is going to determine how much of the original signal survives. Sigma is how much noise is added. At step 0, which we're currently at, alpha is 1 and sigma is 0. And the 5 figures along the bottom are the other representation of this. So it's one window showing all 15 bins and their 5 independent draws of the noise. The white outline, which we can't see here currently, are going to be the original residuals, while the filled bars are going to represent the current state. And right now, the original residuals match the current state because nothing has happened yet. But if we let this animation run, we can see that alpha falls, sigma rises, and these two are always going to trade off. The bright band is where all the 232 windows sit, and we can see that it changes as we move forward. The 5 different colored lines threading through are the 5 different draws through this one bin. And we notice that at the beginning, they all start on top of each other and then spread apart. And the thing that controls that spreading is the random noise we're adding. And if you keep an eye on the bottom row, we notice that the same thing is happening as with our logo. The small bins tend to go first, but we notice that there's this huge spike near 30 degrees, which tends to hold on for a much longer period. By the end, all 5 figures, which show 5 different noise fields, show that they don't resemble the original residuals. So in this case, this is our forward process, and we're adding noise. The schedule driving all of this is fixed, and it's not learned. And this is our training signal. Every one of these noisy states comes with a known answer because we added the noise. The network sees pairs of noisy states and step numbers, and then it'll learn to name and predict that noise. Now we can look at the reverse process. So this is the same thing as in the previous slide, but backwards. So now we're at step 200 on the left, and then we're counting down to 0 on the right. So everything in this case starts off as pure noise from the forward process, and the network is going to learn to predict that noise. The readout also runs in reverse as well. Alpha is climbing, sigma is falling. Along the bottom, once again, the white outline for the true residuals are kept for this window for comparison, and the filled bars show what the network has learned so far. And as this animation progresses, we can watch the big shape arrive, the big spike near 30 degrees arrive first, and then the smaller details fill in last, the reverse of the order things were dissolved in. So now we have these 5 results with the truth residuals outlined behind each one. And we notice that they land in the same neighborhood, they carry the same active latitude structure, but they're not copies of it or of one another. And so this raises 2 questions that you might have. Why do they resemble the truth at all, and why do they differ from each other? So the resemblance comes from the steering we use. So the network is a small multi-layer perceptron, or MLP, which is a stack of fully connected layers. It takes our current noisy state, the step number, and a 4-number vector describing the window. And that vector is the cycle state, which is the smooth sunspot area, the mean latitude and width from the classical model, and the amplitude of the cycle. So the network is never handed the answer, it's told where in the cycle we are, and it has to produce a residual consistent with that. The differences in the residuals come from the starting point. So we choose to sample with a denoising diffusion implicit model, a DDM, which makes every step deterministic. We pick a starting noise vector, and then the whole path is fixed. So the only thing separating these 5 draws is where each one started, and the different starts give rise to different residuals. And that's the point. These are not reconstructions of the truth. They're samples from the distribution the model has learned. Drawing from the distribution many times is what everything downstream is built upon. So now we have both sides side by side, just to show you guys what this entire process looks like. On the left, we have the forward process. This is where we gradually add noise. On the right is the reverse process, where we train the model to predict the noise. And the 2 small figures on the far ends are what I want you guys to compare. On the far left, we have the real residuals of the cycle at this latitude bin. On the far right are the generated residuals, what the model has produced starting from nothing but noise, and these 2 line up. And we can also see this on the figures on the bottom, where t equals 0 in blue matches t equals 0 in green. So the forward half is fixed and has no parameters. The reverse half is learned and steered by the state of the cycle. Both live in the same residual space, which is what lets us put the 2 ends next to each other and ask whether they match, which will be discussed next.
All right, so the next thing we're going to discuss is going over our results. So the first thing we need to establish is our evaluation metrics. Now, there are many ways to evaluate these models, but I will be going over the 2 that we used. So the first is the negative log likelihood, or NLL. This score represents the likelihood of the model matching the dataset, with a lower score indicating a more accurate model. This can be summed up as a correctness of shape, the overall curve of the Gaussian, in the case of the classical model. However, this can mean that the evaluation is sensitive to the tails of the curve, which can affect the metric if the shape is too narrow. In addition, as the NLL is calculated from probabilities and logarithms, its units have no real physical meaning. That's where the Earth mover distance, EMD, also known as the Wasserstein distance, can add to the evaluation. It measures the difference of mass from one curve to another in units of degrees. The lower the EMD, the less distance there is between the modeled and actual center of mass. In essence, this metric represents the correctness of location. Both metrics provide information that can be used to assess the strengths and weaknesses of the model. Therefore, their use in conjunction results in a more well-rounded evaluation. All right, and now we get to the good stuff. This patchwork of plots shows the predicted data from our best experiments across the whole test set. Each window shows a generated universal mean path, with the color scale representing the sunspot density, as can be seen on the far right. The y-axis is absolute latitude, and the x-axis is the years of the cycle. Essentially, this plot is showing the distribution of sunspots across the given cycle, as predicted by each model. So the top row shows the empirical data, which wasn't modeled at all. And then the next is SARG, which is the state-of-the-art model in the field right now. And then the third is our developed classical model. And then the fourth is the classical plus AI model, which uses the base set of conditioning developed for the experiment. At the very bottom is another row of classical plus AI, but with a single draw instead of a mean of 1,000 as the rest of the modeling plots show. Each model/cycle window was evaluated using the NLL and EMD metrics, which are shown here. So as an extension of the previous visual, here is a more condensed view of only the evaluation metrics. The solid line is for the NLL scores, and the dashed line is for the EMD scores. As mentioned earlier, the different evaluations tell us different things about the model. So while the per model scores vary between each metrics, we can surmise that the best model using the EMD is the classical/AI hybrid, which shows a better match of the overall distribution of the sunspots. All right, we've reached the end. So this project wasn't just about creating novel predictive models. It was also about creating a novel approach to research. We collaborated to communicate concepts, come up with ideas, and get to know each other, creating a community of scientists. That complemented the work done with AI assistants to actually refine the data and build our models and assign tasks. The scientific goal of this project was to use the classical and AI models to generate synthetic solar cycles. We ended up developing successful classical and classical plus AI hybrid models that are capable of fitting historical data. And we have promising evidence that AI can learn the finer distribution patterns of the solar cycle. These goals and approaches can be further explored in a future program. As Claudia mentioned, we've had participant interest in ButterflAI 2, which will be launching in the fall. All that we have developed here would be the foundation for an expansion of functionality for our AI model, which will fulfill our goal of using this data to predict the future of the sun. All right, thank you all so much for attending this presentation. It means a lot. We put a lot of work into this. So thank you for taking the time to listen, and feel free to ask any questions in the time that we have left.
Awesome.
Thank you. Okay. Yeah, Andres, you can continue host.
Well, I mean, I think in this moment, if you guys have any questions, I was not able to look but I see you guys have been interacting in the chat. So yeah.
Lauren has a question.
Yeah, so first of all, this is all really impressive, and it's awesome to crowdsource research like this. You guys mentioned there were some papers that were already submitted. I guess my question is for future work, like what are the key research goals that you plan to publish?
Okay, well, I will answer that question. So in this moment, we were focusing on normalized distributions of the butterfly wing. So the plan for the next ButterflAI 2, which is open to anybody, by the way. We're going to announce it in Solar News and everything. We're going to see how many people can we do this at the same time. It's to model the same process, but now also with rates of emergence. So what is the rate of emergence of sunspots as a function of latitude and time? That will be the next step.
Awesome. Thank you.
Nick?
I don't think we can hear you, Nick, even though it says you're not muted. He's going to type it.
Yeah, you can type it and we will answer it. Okay, in the meantime, anybody else?
Okay, here it is. Well, so for the sake of the recording, we can read them out loud. Janet's came in first. Sorry, Nick. So Janet says, interesting effort, but what about the motivation for doing this research in the first place?
Okay, let me take that question too. So the idea of creating a fully realized solar cycle with only very limited information has two purposes. One is forecast. You know, when we're forecasting the next cycle 26, I mean, we're building towards forecasting solar cycle 26. We will not be able to forecast a lot of the properties of the cycle. So having a statistical description of how these things connect to very few information allows us to make forecasts. And because it's intrinsically, like it's by definition a statistical process, then we can also talk about realizations, uncertainties, etc. But we also did this in two steps. One is refined with the artificial intelligence. The other one is a classical. And the idea here too is to reconstruct or understand better what the sun was doing in the past. So as we go back beyond the 1800s, we have observations of sunspots, but we have about 5% coverage total. And so by having a well-defined model that is tied to very few properties, we can also make a statement about those properties, both about filling up what the sun was doing, but also how strong the cycles were, which is a big uncertainty when we go far into the past.
I'm gonna do next question first since he diligently is waiting. So what do you think are other low-hanging fruit in solar, like solar problems that could benefit from this approach?
So this is when we do this part of the reason why we chose this problem is also that you can do it with the resources that are available for free. So some of the students had their computing resources, some were using Google Colab, which is free. And so in the context of an experience like this, a huge part of the equation is how much resources the participants are going to have access to. And so casting problems at the intersection, it's an interesting intersection of complexity and the cost of computation, et cetera. I mean, there are, in the context of COFFIES, there are many things that can be cast this way. But it will have to be done like, sit down and think, which kinds of things. I think, inversions are things that we could potentially explore this way, especially if we are able to break it into two parts. So I think that, bringing AI into a helioseismic inversion or bringing AI into magnetogram inversion, these kinds of inversions could potentially also benefit from a treatment like this.
That's
Thanks. Sign me up for the next class. This is just incredible. I'm really excited about it. I think you guys have done really great work, and I appreciate both the leadership, but also all the participants. It's just, yeah, something that seems really interesting to me. And I'll ask two questions just because I figure I should. One is, is there any way you could get at the asymmetry between the northern and southern hemispheres? And I wonder, because to me at least, that's an interesting problem. And I think it might be something that would be really interesting. And then the second question is more about process. And it is, so you had a bunch of people working on this together. And at the beginning, you talked about the sort of crowdsourcing, collaborative nature of it. Can you identify one or two things that you thought were particularly beneficial that came out of the fact that you were collaborating and multiple people were working on the same project at the same time?
Does anybody wants to take the first question about hemispheric asymmetry? Any of the presenters?
Oh, I can. So we actually, when we were creating the conditioning for our AI models, we had opposite hemisphere activity as one of our contributing factors. It's called opposite hemisphere. So we used that when we were all creating when we were all running our models. It's just that in the end, the base conditioning set kind of won out as our highest performing model. So that's what we included in the presentation. But yes, we did explore opposite hemisphere activity while we were creating our models.
Thanks.
I mean, as regards to, can you remind me the second question again, Todd?
My second question was, you spent a fair amount of time at the beginning, at least, talking about the fact that multiple people were working on the same thing and that you were getting interesting results. And how does all that tie into what did you think was the real strength? And was there anything that came out of it that you thought was particularly useful?
I mean, I think so we had a scoreboard. We were competing against each other. So we had a scoreboard for the classical model and a scoreboard for the AI assisted model. And people submitted their best model for competition. And so what was really interesting, then I downloaded all the submissions and processed them with my AI assistant to understand what different people were doing differently. And so what I think we benefited here from is the randomness of the AI assistants themselves. This is not something most people really experience because most of the people only ask a single question once. They get an answer, and the answer tends to be satisfactory, and that's where we stay. When you have a collective like this, every person gets actually a different random answer, and that influences their own personal rabbit hole. Some of the things that they pursue, some of the things that they refine, the things that they implement. And so at the end, when I consolidated, I was basically taking advantage of that. So for example, one of the participants did a very sophisticated definition of high latitude and the gating of the beginning of the cycle. And so that's not something that came out of any other person, including me. So I took advantage of that. There was a lot of exploration about, like whether we were going to like condition the reverse diffusion processes and combine the idea of unconstrained reverse diffusion with constrained or conditional reverse diffusion. So there were like a lot of the different things that people kind of like pursue based on their own curiosity. And that's the benefit. The benefit is that each person is intrigued by different concepts, and each AI assistance amplifies that randomness and the collective benefits from that.
Thank you.
Janet has another comment in the chat. One interesting comparison might be to use the polar field strength to predict cycle strength and then use the statistical butterfly wing shape for that cycle strength as a prediction. Would that make a better prediction given polar field prediction success?
This is a great idea, and this is something we can explore in the second version. In this one, we kind of assume we already knew what the amplitude of the cycle was going to be. But I think we could explore what happens if we condition not with the knowing what the amplitude ended up being, but the information that we have before that amplitude is set. So that's something we can, I didn't think about that, but we could do it in the second version. It's a really interesting question, actually.
I have a question about the background of, I mean, I know like you showed like the statistics and everything, but in terms of like the presenters here, what level of background in Helio they had built going into this and sort of where they feel like they are now, if anyone's comfortable answering that.
I don't know if Phoebe or Claudia would like to take this question.
Saw Allison unmute if you wanted to start it though.
Oh, yeah. I just thought I might have an interesting perspective on this because I have a background in more biological sciences. I'm the statistic of the person who majored in zoology, but I've always had an interest in astronomy, and that's why I joined HelioHub in the first place. And this whole experience has been really great for broadening my understanding and really getting the chance to work in this field that I've always kind of viewed from afar. And I feel like my understanding has grown so much from being able to from not just being able to collaborate with so many amazing people and learn so much from my peers, but also learning how to effectively utilize AI to eventually have my own personalized tutor. So that's helped a lot, and I'm really looking forward to participating in future projects now.
And then for me, I've done 3 summer research opportunities in like heliophysics specifically. So getting into this, it was still taking on another aspect of implementing that modeling aspect and the machine learning, and then also kind of taking on more of that administrative aspect and coordinating each participant and helping them keep up with the program. And that was really exciting. But I definitely learned a lot, even though I came in with a pretty moderate like background of heliophysics.
I think that one of the things that was really exciting about this is having also, we didn't really advertise it very widely, but we end up with high school students as well, like Swaksh. And, to me, this is personally, I believe that upskilling in artificial intelligence is something necessary for all career stages. And so that's why also I was interested when we started working with Claudia and Phoebe, that it was not just directed at undergraduates, although it was the majority of our population, but that we will open it to anybody. So Shay even participated as well for a significant portion of the class. And so having all different kinds of levels and really seeing how the AI assistance caters to where you are. Like that was so powerful. You know, when I learned as I went through this class as well. I have never implemented reverse diffusion in my life, so I needed to teach myself before I could explain it to the class. And so interacting with my AI assistant, I could get like the AI assistants will talk to you as where you are, and it's really powerful because that means that you have a single person like me trying to teach a very diverse group that hopefully in the next version will be even larger, but the AI assistants and how I condition it will serve you and your like needs much better than I could do as an instructor of a large class on my own. So that was really cool. Okay. Thank you so much.
Thank you,
Yeah.
Andres. Yeah, I was just to say that yes, if there's no question, and also we are at an hour slightly over, and I would call this a seminar end. And thank you so much everyone for presenting and attending the seminar. And I hope to see everyone at our next seminar next month. So see you then. Bye.
Bye.
Thank you, Andres, and thank you,
Bye.
everyone.
Thank you, everyone.